A magnetic force is exerted on single charged particles when they move through a magnetic field. In this unit, we examine the forces exerted on a current-carrying wire when placed in a magnetic field. One way to do this is to place a wire between the poles of a magnet, as shown. The magnetic field is directed into the screen. When no current is flowing through it, the wire remains vertical. However, when we induce an upward current in the wire is deflected to the left. If we reverse the polarity such that the current is directed downward, the wire is deflected to the right. We can conclude from this simple experiment that, just as with single charged particles, a current-carrying wire is subjected to a magnetic force when placed in a magnetic field. Since single charged particles do, it is not surprising that a current-carrying wire experiences a force when placed in a magnetic field. It is not surprising because, in fact, a current is simply a bunch of charged particles in motion. Consider the positive charge carrier Q moving at a drift velocity v sub d to the left in a uniform magnetic field. How many charge carriers are there in such a segment? The total number of charge carriers is the number of charge carriers per unit volume times the volume. Let n be the number of charge carriers per unit volume. We know the volume of the wire segment is its cross-sectional area times its length. Thus, the total number of charge carriers is equal to the number of charges per unit volume times the cross-sectional area times the segment's length. A charged particle traveling through the segment has an upwardly directed force on it. Verify this using the right-hand rule. From the previous section, we know that, for a single charged particle, this force equals the cross product of the charge times the velocity and the strength of the magnetic field. It follows that the force acting on a current-carrying wire equals the force exerted on one charged particle times the number of charges in the wire segment. The formula for the force exerted on the wire by the magnetic field looks complicated. Fortunately, there's an easier expression for it. In a previous unit on current, we learned that current equals the number of charge carriers times the charge per carrier times the drift velocity times the cross-sectional area of the wire. Substituting in this equality here gives us the simpler expression. Force equals the cross product of the current times the length of the segment and the magnetic field strength. Recall that the magnitude of the cross product here is the product of the magnitude of IL and B times the sine of the angle between the two vectors V and B. What is the current in a wire that is 4 millimeters in diameter if there are 5 times 10 to the 30th charge carriers per cubic meter that are drifting along at a rate of 3.42 times 10 to the negative 4th meters per second, each with a positive charge of 1.60 times 10 to the negative 10th coulombs?
Correct.
How much current is flowing northward in a horizontal 10-meter long wire if a uniform horizontal 2 Tesla magnetic field crosses the wire in a northwesterly direction at an angle of 30 degrees, producing a force of 45.9 newtons?
Try again. Correct.
Recall the equation F equals the cross product of L, I, and B. As discussed in an earlier section, force, current, and magnetic field strength are perpendicular to one another. Therefore, your thumb indicates the direction of the force, your index finger the direction of the current, and your middle finger the direction of the magnetic field. Which way is the conducting wire pushed by the magnetic field?
Correct.
Here's an interesting application. Suppose that you dangle the lower portion of a square wire loop in a magnetic field, and then induce a current through the loop. Let's apply the right-hand rule to this setup to find the directions of the forces acting on the 3 sides of the wire that are in the magnetic field. The X's indicate the magnetic field is directed into the paper or screen. Dots indicate the field vectors are coming out of the page or screen. The forces on the vertical sections of the loop are directed outward and cancel out. The force on the horizontal wire is directed downward and is at a 90-degree angle to the magnetic field. What is the magnetic field strength if the current flowing through the wire is 1.56 amperes and the measured force is 0.233 newtons?
Correct.
For a current loop in a magnetic field, use the right-hand rule to verify that, for some of the loop, the force from the magnetic field is directed out of the screen, and for the rest of the loop, the force is directed into the screen. In this situation, the current goes out a certain distance and then returns. The outward force results from the current's movement to the left, and the inward force results from the current's movement to the right. These forces cancel. In a more mathematical treatment, the sum of all the segments of the loop adds up to 0. What is the force acting on the straight portion of a semicircular loop lying in a constant magnetic field?
Try again. Try again. Correct.